So my pleasure to introduce Lina. She's Winokur Professor at Harvard of Electrical Engineering. She's received many awards during her career, such as the NSF Career Award, the Air Force Young Investigator Award, as well as the ONR Young Investigator Award, the Donald Ekman Award for Best Young Researcher in Control, and the IFAC Manfred Thoma Award. Her work is in control learning and optimization, and today she'll talk about her work on representation learning for control of dynamical systems. Thank you very much.
Thank you for the introduction, and thank you everyone for coming to the talk. So we have been listening to so many great talks. Thank you for everyone doing a wonderful introduction to RL, making my talk be much easier. So a very quick motivation for this community. There are a lot of talks today. I think the one common theme is how we can actually translate the success of AI or deep RL to the real physical systems. And we have already seen many challenges, so I will go quick. This is some summary of the challenges. It's actually more than this. So first, about the data. When we look at what have been the big news success, it's mostly about computational systems. Even large language model, you do everything on computer. If we want to move those success to the real physical system, as a power system, transportation, and also to change the future system, like what the data we will have. People want to talk about we can taking off the traffic signals, but do we have a data, like if without traffic signals, how the driver is going to behave? So the data quality and where to get in the data is owned by different companies, a lot of issues. So first about data. Second about computation scalability. So computation scalability, we talk about sample complexity today, and it's also previous talk talking about convergence, global optimality. And there's another challenges. If we talk about the real physical system, it's not just a single robot system in the lab. If we think about power system transportation, so we have sensors at different locations, and sensors taking the measurement, sending to decision maker either be edge computing, sending to the cloud, sending back to the command. So we would like the decision making can be done quicker, but they can also coordinate, like how we're going to do it. There's a limited sensing, computation, communication. The other one, safety. We listened to Alejandro's wonderful talk about constrained RL, had a nice discussion about the safe RL. What exact safety do we mean? There's a lot of challenges. I will probably touch a little bit. And last one, when we try to really bring the RL success to the real physical system, one challenge is, I put in some examples, is what's really exact the goal we want to achieve. Even for the single agent system, like typically, the objective function is not like well-defined. So we need to figure out what should be the reward function for the individual agent. And then the more difficult challenges, if we have a multi-agent system, Kai-Jin do a wonderful talk for the multi-agent system. What if the people's interests are different? Are we going to align them? Or are we going to align them? So a lot of challenges. I'm not going to dive into one by one. Today, my talk is trying to focus on representation-based approach. So what is the representation approach I will talk about coming 2 slides. I also want, if I have finished my theoretical talk within the time, I also want to dive into concrete application to show the gap between the theory development and the real application, what additional thing which can do, not just doing the representation. We can use the system structure and the knowledges to further improving our algorithm design. Now, let me talk about, so what's really the major problem I want to focus on today? So I said representation. And my background comes from control. It's wonderful to actually follow Baham's talk about actor critique. It will come in again in my talk as well. So my goal is, from the control textbook, we're doing the nonlinear control. This formula probably is very familiar, except that I changed the state notation from X to the S, from the U to the A. So this is the state, and we have a state transition, has a control action. We have the state dynamics, have the process noise, and we would like to either minimize the cost or optimize the reward. And the goal is trying to find the policy. We can do the find time horizon or the infinite time horizon, name the averaging case or discounting case. Let me just stick to the discounting case for the formulation. So for this is a very standard nonlinear control problem. If we dive into the literature, so if we think the literature reasons is because we put in the survey paper here rather than like if tracing back 1950s, 1940s, like we started with thinking about those problems. So there are a lot of different methods have been done by our control communities. And for those who has took those nonlinear control class, and when you do run the simulation, you will see like for different methods have a different limitation. And if I pick in the SOS tool, which I learned a lot during my PhD, it can only handle very small scale problem. Like it's very difficult to find what really the LMI I should have, and what's LMI going to be a large dimension, it's very hard to solve. And recently, I think the Koopman control trying to change the problem from the nonlinear to linear. But if you really dive into it, if I add in the controller into my system, my Koopman control will still have nonlinear component. So putting all those summary, I think that today the talk I want to, like the big motivation when I started this topic is, can I kind of just, like people had a debate whether RL is a good approach for control or not. I'm not going to talk about this debate, but if I just think about all those wonderful computation tools have been done by those deep RL community, can using those at least as a computation tool to test on those nonlinear control problem and to see the performance. So kind of how we get it started. So today I will talk about 3 components. First, I said I just want to use it as a computation tool, even not talking about learning. I have a model, I know this is dynamics, everything I know. I just want to developing a general nonlinear control tool that I can plug in, put in my state space representation, and give me what's really the optimal control, or like some control are going to do the work. And once I finish that part, I will dive in. Typically, we actually don't really have exactly the model. So can we actually develop in data-driven method based on the representation? And lastly, I will talk about how we're going to add in some robustness and safety to further close the gap between the algorithm and the real application. Now, let me dive into the first part, the representation-based control. So a quick review of the MDP, because I'm going to connect with the control and RL. So the MDP is kind of very similar framework as using the state space model. We have the stage, state, action, state transition. One thing I want to highlight, here is state transition compared with the state space model I talked about before, which is ST+1 equal FSTAT. Like typically in the MDP, we write it down as the transition probability, which is a P. So state reward and policy, trying to find a policy to maximize the long-term reward. This is almost exactly the same as the control problem I just provide. And for the RL, there's so many different methods. It's typically you have the agent, the learner, going to interact with the environment. Probably even don't need to know the model. Just keep trying different policy, like the active critique algorithm. So yes, indeed, this is it's wonderful to follow Bahama's talk. I don't need to do too much introduction. Like this is one popular method, and with Alex and Bahama's wonderful contribution, we also know the method is going to work. So with active critique, typical the framework is this. We maintain the policy, and well, we don't know what is the policy structure to start with. Like, go ahead, pick some deep neural net to parameterize it. And then for the critic, try to evaluate how good the policy is, because for my policy gradient, I need to use in the Q function to approximate my policy gradient. So this is, again, we don't know what's really the parameterization we should use. From previous talk, there's one question I was planning to ask is where those linear approximation come from. Right, so typically people just go ahead to doing the deep neural net parameterization, put in the QW. W is the parameter from the neural net. You can do the linear function approximation or doing more complex function approximation. And then it's going to be the iteration between the critic evaluation, active update, keep running it, and waiting for the algorithm to converge. So this is a nice framework. I highlighted the DNN component. Is when I was studying, like looking into the RL, trying to play with the code by myself, it's very difficult. My students are here, like I was always asking them, can you send me the code, why the code didn't work on my computer? And there's a lot of frustrations. So the question, like, especially one big question for a person like who hasn't really had too much DNN training is, what's really the DNN we should pick? Is there a systematical way I can draw? So like, that's a question. Can we have a systematical, simple, and we can actually have some theoretical guarantee? This is actually well work. This linear approximation actually will close to your true function. That's a question. Hope this question is clear, because that's the most important slides, the coming couple slides. Like, putting that question, then let's revisit. All those methods, the most important part is the Bellman update. Right, the Bellman update is whether you put it on the V or put it in the Q, is you go ahead to put in the iteration. So the Bellman update, put in I want to evaluate, given the current state action, I take a policy pi, how good that policy is. So you put it for the limit averaging, discounting infinite time horizon, I have this kind of fixed point part. Then we put in here. So this is the key fact. If my state transition, look at this one. So in the probability transition language, given the current SA, probability of the next S prime, has this decomposition. So if you dive into this decomposition, it has a two component. One is a phi SA, the other is mu S prime, linear decomposition. So if it has this, and I can call the phi and the mu as the feature maps. So why talk about this? If I have this one, now I substitute this probability distribution into my Bellman update. You don't need to worry about what really the V is. I'm only using one property, is the linear property of the integration. So I substitute my those kind of low rank or like the decomposed P into my Bellman update, writing down my Q function. Look at here, like it's actually just one step liberation. My Q function will stay in the same linear space of the phi SA. You need to augment the RSA. Like I said, right now I'm dealing with a model-based case. I know everything. I mean, the reward function, typically we design, we have it. So why this method? One thing is answer the question from the previous talk. That's actually one kind of phi I can use. And I just go ahead to learn the W. I can apply Alex result to put in the active critique method. So, but indeed, in the RL community, there's a lot of both theoretical research and also some empirical work, like you put in the linear representation, the linear function approximation to developing the efficient method. It has theoretical guarantee to show how much more sample efficient. If I know my state transition probability has this low rank representation with the two feature maps, one the phi SA and the mu S. And so this is probably the most important slice, but this is a one caveat, but this if. So where is it coming from? Is it true that's actually given me a system, nonlinear system dynamics, I can find these things? That's when I was looking at those paper, that's a question in my mind. Like I cannot just start with that assumption. I have the state space. Like I know the inverted pendulum, I know those dynamics. I don't have this. Now let me take a little bit detour, right, to give you where this comes from. Indeed, we actually can find the representation for that. So a very quick introduction of the positive definite kernel. Alex also talking about kernel. So this is also a similar kernel. And if we have the positive definite kernel, what you can think about is just a matrix. You can take in the two-dimensional input, x and y, like two kind of input, and it's positive. So the Gaussian kernel is one of the positive kernel, is always going to be positive definite. Why talk about it? It's this. So if I have a positive definite kernel, and from functional analysis, the real analysis, like for the one of the theorem, Bologna's theorem, will show this kernel can be represented to, you can think it as an inner product between the psi and psi conjugate. It's natural. So what's the connection with the nonlinear control problem we're talking about? Look at this one. This is the dynamics we have, this is a standard state space representation. Let me assuming the noise is a Gaussian noise. We can talk about extension later. If it's a Gaussian noise, I can write it down my state space into the state transition probability using the Gaussian kernel. I put in the Gaussian kernel, and I mentioned before, for the positive kernel, it naturally has this decomposition. I substitute my Gaussian kernel, but look at my Gaussian kernel right now actually has an F function. If you ask where the F play a role, F will show up in the feature space. So I using the Gaussian kernel, and I using the Bologna's theorem, I can do the decomposition. And what's the feature I talked about earlier? Now my goal is I want to find what's really the VSA, the feature space I can use, I can go ahead to run whatever IO algorithm. You can also do deep Q learning because sitting in the same space. So indeed, like put in conclusion, we have a linear decomposition for our nonlinear control dynamics. Feel free to ask questions during the talk. Hope it's convincing. I didn't do any approximation so far. Everything is exact. But there's a one caveat, is if I'm using this real analysis theorem, this representation is infinite dimensional linear feature decomposition. Like it also didn't really bring me anything. This is the infinite dimension. If I'm aiming for a computation tool, I haven't really got a computation tool yet. So natural thing you can think about, right? Okay, since you have infinite dimensional, go ahead to do the truncation. And that's kind of where come from the linear function approximation. You will have a gap. But the good thing is I start with, like I know where my representation comes from. If depending when I really run the analysis or run the algorithm, depending how the performance look like, if it doesn't really working well, I can go ahead to add more feature. And what feature I need to add? So the two different truncation methods I've been doing, I have a principled way to tell me what's an additional feature I'm going to add. So let me give you a quick introduction of the two different feature truncation method. First one is very natural. It's just go ahead to the random feature truncation. For the random feature truncation, as I showed, the linear decomposition is an inner product. Actually, that inner product defined by the rho omega, that's random probability distribution. You just go ahead to sample the feature according to that probability distribution. And pick the number you want. Now we got a finite dimension approximation. And that is my feature approximation. And the one nice thing is the tool I was talking about here is actually has a huge literature in the kernel machine learning. Like before the deep learning taking off, the kernel machine learning is actually kind of one of the popular topics. There's a lot of tools. So when we develop the theoretical analysis, we actually can build upon the previous study. People has studied how many features I need to have if you want to achieve certain kind of approximation error. But everything is already provided by the community. And this is just random. If I want to do better, like I said, this is the analogy for this particular kernel is the positive definite matrix. You can do the better spectral decomposition to rank them, pick the top features. So that's called Nastrom feature selection. I go ahead to pick the top features. And again, how many features I need to have? Now those eigenvalues will tell me. And because I'm doing the full model-based thing here, I can do all the things offline. So with those feature representation, my Q can be staying the same feature. I can go ahead to implement any kind of IO algorithm as long as they need doing the Q evaluation. We have been seeing a lot of talks today. A lot of talks is either you're doing the deep Q learning or you're doing the active critique, the Q evaluation is one of the key. So like this is a framework. You can first find the feature. It can be either the random feature selection or the natural feature selection. Then I can parameterize my Q using this feature function. For the update, if I'm doing the active critique, update the theta and updating the critique. So it's very natural, it can fit into any kind of IO algorithm. So let me show you the simulation. Indeed, for the simulation, we're putting our representation to the open source tool, SAC, soft active critique algorithm, and to see the performance. So first, we start with the control test, which we are familiar with. We also have some other like more open AI gym tests. Later I will show you. So this is for the inverted pendulum. As I mentioned, so we actually start with compare with the control method, ILQR, iterated LQR, and the Koopman. I will show some figure, like the data later to talk about the performance. When I was given this talk, like previous time, so some people who are familiar with ILQR say, like, why your ILQR is not performing well? This is the one thing we actually like is, I start with talking about stochastic nonlinear control. The ILQR actually will work well if you don't have any noise, but in reality, you always have a noise, either from the measurement, from other things. Once add a noise, ILQR is actually not robust. So that's what happened for this simulation. And we also simulated for the quadrotor. And for the quadrotor, similarly, and we actually try to see if I add feature, how much improvement my performance will have, and to kind of benchmark with our theoretical analysis. So this is kind of the number I put in here. You see I have put in the non-noise case, noise case, and we also add another. This is the challenge raised by one senior control professor asked me to compare with the Pandelbot, which is an arrow bot in the OpenAI. It's double-inverted pendulum, undirected system. Because in the 1990s, I think there was a competition in the control community try to find who can do a better control. It's like for the entire control loop. So we picked the paper. Hopefully this paper was the best result from that time period. And to see whether our method can compare with that one. And you can see, especially once adding a noise, so our method will achieve much better performance. So as you can from our representation, our method actually embrace the noise, stochastic. So it's very different from the energy-based method. Almost adding noise is actually very difficult to really think about the energy function, how you're going to find a controller, minimize that. So theoretical analysis, this afternoon talk, I'm not going to dive into details. And just want to say, theoretical analysis for us has compared with the previous talk, we have another component. Another component is approximation error caused by the feature truncation. And also, we cannot really do analysis if I really parameterize by those deep neural net of the policy. We actually did the natural policy gradient by using softmax parameterization. And that one, the natural policy gradient, actually in a very clean form. So we know what's really the method it is. So that kind of difference compared with the previous talk. If you are interested, so the result is available online. You can check how this, so we have a few components. One is how many truncation, the feature we need to pick. We need to decide for the Q evaluations that we have based on the sample-based method. And we also have the policy update. So it's kind of 3 components adding up will cause eventually the ultimate error bound. Any questions so far? Good. So now let me talk about other this is first we're feeling excited. Okay, now we can if people give me the model, I can give what's really the controller. But what if I want to use the method for the true robot, for the real system, which I don't have exact model? So the way to extend it, one natural way, is I can just build in those probability distribution for a set of function, the f, which then we can use in Alex tool this morning, how to do the posterior sampling of the f. That's one direct way. And once I have the f, go ahead to do what I just showed, picking those features through those kind of Fourier transform. But there's another more interesting perspective, try to understand what this representation means. So the representation actually doesn't care, I would say it's care if you know the model, but if you don't have the model, right, what it's really trying to do is to making the state transition as A to the S prime into certain feature space representation. So I can use the data directly to learn this representation. But I don't need the F. What I need is a PSA. So this actually raises a question. So we have papers using this method as examples. But I would say there's a lot of things still can dive into more detail. So what exactly the sampling? Can we have even better theoretical guarantee? So that's if you're interested, I'm happy to talk more because this is the ongoing work we have been still working on now. So there's some examples. You actually can have some other method. If I look at this feature representation, what's it been doing? You can actually, if I talk with dictionary learning people, this is dictionary learning. So you have a phi SSA, and you're going to put in the phi SA and the mu S prime. And then I can put a projective function, the first one is just putting the loss function, and you can argue that it's not really not convex, and it's also not unique. So it has all those issues, but it's actually big into the ML problem. It actually can fit into different kind of ML problem. And you can also view those as a tensor decomposition problem. You can view the P as a kind of 3 input tensor, and I want to put in this tensor into the low-rank tensor. One is using the 2 input, PSA, the other one is mu S prime. So you can also use the tensor decomposition and put in this as a probability space. We can use the MLE, this one method. I can also just directly view those as a singular value decomposition, like how we're doing for the positive definite metrics. So this is just kind of a few options you can go. And for each one, we'll come with different pros and cons. Not going to dive into details today. This is one challenges when we really do the data-driven one, exploration. Right. So I don't know the system. So I using the current data, I learn the feature. It's definitely not enough. I implement the policy. I go ahead. I need to figure out a way, how can I get in the new data? The new data is going to help me to learn the feature. So I just give you the ideas. So first, if I do in the model-based approach, I do the template sampling, similar to what Alec was talking. You can add in like even better information-driven way to pick the feature. And when we're doing the pure representation-based learning, so we tried one method is rather than think about that one. So eventually, how we're using the feature is to learn the Q, and from the Q to learn the pi. So when we update the Q function, we add additional bonus function, like the UCB, upper confidence bound, this kind of method, to encourage the exploration to getting more knowledge about the feature. So this is a few examples. So we tested on the OpenAI Gym and on different tests. We had those kind of outcome, like the different performance for those data-driven methods. I don't want to spend any time to talk about this numeric simulation because I think everyone has experience. Depending how you're going to really run it, sometimes so is the result significant enough, not significant enough? There's a lot of discussion. But I want to put in this, like the linear representation is a nice way in the sense of it can even further, like I talk about how to balance exploration and exploitation. But let's dive into more. I was using the sim to real to talk about how the linear structure actually can be used to making my exploration even more efficient. So what exactly, I'm using this one to talk about the linear space. So when we think about, like this morning first talk, he didn't use in the sim to real, he learned the robot from scratch. So let's look, if I have a simulator, for many applications, we actually had a very good simulator. So, but the real situation is different. I'm focusing on only one gap here. It's a P naught and a P. So I have my parameter, my kind of simplified model, and then I would run my algorithm, deploy the policy to see the outcome. So like the bottom line is, if I use the my representation approach, I will use the P naught to learn my feature, but that feature is not really exactly the feature maps for the reality. Like summary, what I said, right, is I can use my method, since I have a simulator, I can learn the feature. I mean, you can even have a treat as a generative model, you can learn it. And I can, using that one, I know what really my Q function is. Now the real world is different. So there's a gap between the true P and P naught. With a gap, so if I want to go back to think about how to really learn the feature, I would say that's the advantage of the linear representation, is rather than to just forget what you learned before, I just look at what I need to add to my feature space, the additional part. Right, so, and then my Q, because it's kind of sitting in the linear space, think each one as a basis, I just adding more bases. So adding additional bases, go ahead to updating your W, omega. And the question is, how can we learn a new feature more effectively? Since we stayed in this kind of linear feature representation, one natural way, right, if you don't want to waste the representation that you learned from previously, one natural thing we can add, and put it here, think about the span, right? So each feature, when I say feature, is actually a sequence of features. This is a feature that will fit in, like tells me this is what able to represent is the function space span by what's the feature you learned before. And what I need to learn is to learn a new set of features, and that will kind of adding additional bases will expand the space. If I don't want to waste the representation power, I can add this. The new feature I'm going to learn, I would say is go to be orthogonal with the feature I already have. Because for adding, like if it's not orthogonal, the information already captured in the previous feature. By doing those, it will actually use the sample more efficiently. Let's look at when we implement in the real system, how it works. So from the sim to real framework, if I summarize, so the way to do it is you have physical simulator, first step, and you learn the representation. Once you learn the representation, the representation I learned is a phi. I can like run my initial policy. Initial policy typically not going to run well. I'll get new data. I get a new data, I will come back to improving my feature, adding more feature. And then you go ahead to run your RIO algorithm, have the new Q function update. So I look at how it's been, and this kind of, we did an active critic update, how it's work in reality. So we simulated, this is the first just directly simulate the simulator policy. because the gap is not really going to work that well. So the test is actually not that difficult, just hovering, stabilizing, and then coming back. So we had like one step updating, using the same feature, but let me updating my Q and then getting a new pi. It's doing better, but not good enough. And eventually, we did our sim to real framework. We update the feature and also update the Q. And this is the performance. We implement this. This is the more numerical data to show. And we also try this for a little more complicated tasks. I try to do the treasury check-in for figure 8. It's very hard to tell what's really going on with the simulation. And you will see the plot. To tracing the Q, this actually can raise one interesting discussion. Typically, we test RL, you put in the reward function. But what does the reward really means? And even the reward is very high, probably performance still not really that good. Like for instance, you look at the built-in baseline. So this is chasing an 8. The arrow is not really that, it's actually good. But you look at this 8, especially for this component, it's not really exactly like an 8. And this is from our policy, like it's more 8 shape. So this is another one, usually every time people will say, if you design RL, your reward function, but how exactly reward function can really capture what you want to achieve. Obviously, this is still open question. I don't have an answer for this, but this is what if like a simulation, like you cannot just look at the number. So now I almost finished my talk. Like the last component will be very quick, is the representation, if you notice, right, it's just kind of a way to rewrite my state transition, and that will give me the computation advantages. So then the natural question is, if I further put it into the real physical system, I care about robustness, I care about constraint, can this representation be useful for those as well? Or like probably we're making those things much challenging. So that's why we look into robustness and safety. So for the robustness, we start with the standard formulation. Right? The robust people talk about is if you have some dynamics reward, you have the perturbation, you don't have an exact model. Like can I developing a control policy that's doing the worst case within this class, and then how the performance look like. And the constraint, Alejandro's talked is very nice introduction for the safe RL, the constraint RL. Here I only put in one constraint. So this constraint I put in here is the D. Let me introduce this one. Is the state occupancy measure, right? The interpretation actually can also train to be some other thing. So the interpretation for this one, like if I want eventually my system stay in some kind of state, like you can put in the distribution, like if there's some very risky area, you can put in like 0 probability there, and some other area you don't care, okay, so you can go there or put this ideal shape you want to achieve. So this is one example of the constraint. So here we can put in the distance. You can say KL divergence or some other thing directly on the occupancy measure. So the one reason why I put in this, the constraint directly on the occupancy measure. So in the next slide, I saw some audience taking the photos. I'm happy to share the slides, so don't worry about the slide. So now, this is one reason I put in that as my representation for the safety constraint. So the occupancy measure, from the definition, like is similarly, it also has this kind of Bellman like equation in recursive way. If I have a one-step state distribution and what's the next step state distribution, using the state transition probability represented. The one interesting thing is from all the previous talk, I only using one part of the feature, which is the phi SA. My original, when I do the feature decomposition, I have a phi SA and a mu S prime. So this is actually where the mu S prime will show up. The mu S prime is a feature for the state distribution. If I recap, the phi SA is a feature space for my Q function, but the mu S, that feature is going to be the feature space for my state distribution. So from the occupancy measure, and this is kind of similar, just one-step proof, and what is being used is integration has a linear property, and that's the mu S will come naturally. With that is we had a lot of algorithm from Alejandro's like constraint RL. So this is one constraint RL method we took from literature. You're doing the primal dual, right? You're introducing the dual variable. And then you have the kind of two-loop update. You will have, like, in the inner loop, for the primal problem, you're doing the critic update using the phi, constraint critic, like try to understand the state distribution using the mu, and doing the actor update policy gradient, putting that. And then for the dual variable, using dual variable, like just constraint violation using that information. So this is overall, and you can actually, again, the tool I provide is representation. You can use that for other methods as well. And I'm talking about robustness. So robustness is actually much more difficult than we thought about. Is like originally, like the representation will still show up, and then I can use the representation, put in the low rank decomposition to bring the computational efficiency. Fortunately, it's actually difficult because if I dive into the robustness, people just put in the robustness, right? Just put in perturbation. But if my robust representation RL is also adding perturbation, that means I need to figure out perturbation on all the state action space, which is very large. So I'm not going to tell you how we're going to deal with it. Rather than to start with the original robust MDP formula, we look at, with representation, that is my IO method. And for the internal step, we add robustness evaluation into it to improving, like kind of focusing on the perturbation, on the efficient, like on the important part, find what is the effective perturbation. So the paper, I think we had all the paper on ICAF, so you can take a look. So the numerical result this is still ongoing work. For the safety, we put in some constraint on the safety, actually swing from the unsafe region to the safe region to see whether it can stay in that safe region. And indeed, the algorithm, like once it's reached, the algorithm will figure out the policy to stay in the safe region. And for the robustness, we run finding the policy using the nominal mass 1.0, and then evaluate for the cases with a different mass. And you can see with our method, the performance will be much better than the non-robustness version. So I think I have a few minutes, Alex. Right. So like that kind of concludes the talk. Like for the representation, I put in summary, I start with the model base, right? If I have system parameter, everything, can I just developing a toolbox and people just inputting, that is your state, like this is state space, and then this is the outcome. So we're building the toolbox right now, like hopefully you like the CVX, you just need to writing down your equations and you are getting a policy to start with. And then if I have more complicated thing, like how we can do in the data-driven and the robustness safety, like adding all those components. Any questions? Because I want to spending a few minutes talk about once for the real application, since it's actually more complicated than what I was talking about. Continue? Okay, good. So this one will be, you can relax all pictures, so no equations. Like for the application, so I have been reaching out by different people. Look at this application set. It's building designer, and the second one from the MGH is a radiology lab, and the last one is a bioengineering, like on really the molecular biology. So different application, and all of them actually can connect with the learning-based control. The first one probably is more connected to our control community. We have a house. Well, is it a real house? Is it a location? Everyone is welcome to visit. So it has a lot of sensors. If you want the data, so the data is able to share. We have a full 2-year data able to share. If you're interested in this one, please talk with me. So we have the smart window and smart the tab and all the things, all the sensors. The goal for us to do it for this one is not just thermal comfort. We also worry about air quality, the CO2, the natural ventilation. And the controller for the natural ventilation is like the window is actually automated. So it can turn on, and we can decide how many degrees being turned on. So for this, we have been working actually for a decade for this project. There's a lot of engineering things going on. So we did a model predictive control. We also did a model free, and I can discuss like eventual outcome, what exactly. We actually eventually did implement the MPC. So, but for the MPC, the one big question is the dynamics. How are we going to learn the dynamics? So this work was done before I did the representation learning, so I probably will put in my representation to see the performance. So then we were looking into like the biggest difficulty is the ventilation dynamics. It's very complex, it's air fluid dynamics. So we also need to kind of control the building like for like entire year, like the seasonal change, and like Boston today is nice weather, sometimes you will see it can change very quickly. So we eventually pick, this is the model we actually did. We ensemble a few deep learning model, especially the LSTM. So we had the short prediction for the ventilation. We also had the long prediction for the thermal mass. Putting them together, so the outcome is we actually say we're able to improve in the thermal comfort by 80%, and the ventilation is also like 60%. I'm not going to give you the more equation, more picture here. And this one is a collaboration with the radiology department. They reach out, want to build an autonomous ultrasound machine. So what's this use case? A patient feeling uncomfortable, go to the hospital, will do CT, MRI, a lot of like 3D scanning, and let's say unfortunately find a tumor. So typically the follow-up will be half a year or 1 year, which is very not frequent, which for certain disease is not ideal. So the collaborators were like, hey, can we put in the ultrasound? And the ultrasound is, I had ultrasound experience scheduled for 2 months, and I don't know why, but that's one reason I want to do the autonomous ultrasound, then patient can get an ultrasound more frequently. So I can have like one good thing, typical those patients have some existing knowledge already. And I do the ultrasound and go ahead and then probably send it to the doctor to see what's going on. Originally, I think it's a very simple control question because manipulator, I don't worry about the time, and I don't need to pick up anything, should be easy. And once we started, I like, this is a very difficult. First challenge is, this is like perception-based control, but the perception comes from the ultrasound machine. The quality is very low. And there's no map. Like if you ask the robot to understand the human autonomy, it's difficult. I don't understand the ultrasound image. And we also need to run the real-time biomedical imaging processing. Like you don't need to like wait for another like 10 minutes, 20 minutes. The patient will lie there. They don't want to waiting for like 2 hours to finish one ultrasound. And another safety concern is a false control. So again, I'm not going to tell you exactly that eventually what so many different solutions we combine together. This is the stages we're doing. The initial contact is actually relatively straightforward. We can use in the computer vision-based control, like using the initial contact, finding where the target is. This is a real human phantom. And the map is actually really collaboration with the radiology department. We try to find what's really the line marker I can use to build a map. So we decided to use the hepatic 1 as the line marker to start with to build a map. And there's a lot of deep learning going on for this one to eventually build a 3D coordinate dimension. And the last one is actually the reinforcement learning. Once I have the map, it's not going to be exact accurate. So I will go ahead to think this is my target location, which usually is probably not. So we figure out the local justification, like to locally updating my control action to find the imagery matching. So this, like, we actually took us 3 to 4 years, more than 3 years. Eventually, we had the videos that I'm able to show. You say initial contact relatively straightforward. Now, once they have initial contact to find the landmark, so you say once find landmark, he really needs to do a lot of exploration. So once it has some information, linking starting with that, and then starting that point to build a map, you're getting more images, do this construction, the 3D, haptic 1 model, matching them, and then using the target CD images to figure out that should be my target of the tumor. Go there and try. You say try to match with the target image that we think it to have, move into the target, and circle match. Like it's like again, I put in this as an example to show. I think for the real thing, is always will be more challenge, but on the other hand, we have more domain knowledge can help. The last one will be very brief. So this is a different dimension. It's about to grow an artificial cardiac, a heart tissue. So we grow the heart, so my collaborative bioengineering has the stretchable nano-electronic device, can plug in to the tissue, soft tissue, and can grow with the tissue. So we use this to really grow a heart tissue so that you have the skin cell trying to be stem cell culture to the initial heart based on mature. So we want to figure out the stimulation policy to eventually stimulate the heart tissue, make it be functionable. So when originally, I think this is a standard IO problem, but this is probably the most difficult one because of data scarcity. To finish one experiment, it took more than 60 days. It's very expensive. And each time, the postdoc can only do 3 tissues at the same time. And that is already more than 2 months. So we struggled, and my student here, so he's very creative, like tell me, Lina, we should just give up IO method. Like, okay, then what method we can do? So also like the one natural thing for that question is what should be the state, what should be the reward? We don't know. And then the action is kind of more straightforward, like electronic stimulation. So the algorithm, we eventually give up the IO, and we did our own batch Bayesian optimization. So the bio paper should be coming out in 1 or 2 months. If it's available, I'm happy to, if you reach out to me, I'm happy to share once the paper is ready. So in the end, I want to conclude my talk. So as I put in the more theoretical work to talk about how can we actually rewrite the state space into a new representation that bring us the benefit. And then I put in the concrete application to see how we actually, the problem become more challenge, but we have the collaborator, we can put in all this knowledge together and to eventually get in the outcome and it's going to work. So thank you, everyone, and thank you for all my collaborators and my students for the wonderful contributions. Thank you.
Thank you. Are there any questions? Yeah, someone's coming.
Great talk, Lina. Thank
Thank
you.
you.
A question. Sometimes with the linear approximation, right? So you may need many points, many linear segments in order to get a good approximation. Sort of you mentioned that you have a method of adaptively selecting how many segments. If you didn't care about global convergence and you were happy with sort of some local convergence, would the nonlinear approximation, and now it's possible to use neural networks to approximate. Any comment on that?
Great question. So one clarification is for the feature I put in here, it's not linear segmentation. It is nonlinear functions. So it's, let me put in this one. Yeah, here. So if I model it, first of all, the FSA, depending on your original nonlinear system, it's nonlinear. We don't do any linear segmentation. And when we're talking about the linear representation, is linear with respect to the nonlinear features. So my feature here, the phi omega here, is everything is nonlinear. And for the second step, like this is from the model based, and those kind of psi omega is cosine sine. And then for the data-driven part, the way we did is we actually using the deep neural net to represent the phi SA to get started.
But I guess my question is, why do the decomposition? You could just use a nonlinear approximation and not write it as sort of a linear combination.
Yeah. So I see that question. So then now the question is, when I translate here, is the linear representation back to here. Right, there's another possibility you can go ahead is for the Q function, right? Don't do this kind of linear, fix the phi, just learn the W. You can just go ahead to learn the parameter for the entire the deep learning, and that's indeed what people have been doing, right? Even for this question is when I started is you still got into the question what things you're going to get started with, which the nonlinear function you're going to use, because a lot of choices. And on the other hand is there is for this method is when I go ahead to learn the Q function, because the phi SA is being fixed and I know how good the quality is, and learning the W from the previous talk, that's why we did the least square. So I know that doesn't really lose anything. So the answer will be I can definitely do very heuristic. And there's another option. I don't need to do that many heuristic. And I know where to I have the nonlinear, but where the nonlinear come from. So that's the kind of that's why I call it principal systematical way for me to tune, design my toolbox. Yeah, but indeed, you can, we start with doing the general toolbox is 2 layers, each layer has 256, and you pick in different kind of neural architecture. Sometimes it works, sometimes it didn't work. If it didn't work, you go ahead to pick another one. But now you actually, okay, if this doesn't work, I know that just add an additional feature of design. So it's at least making my life like much better in the sense I know what I'm doing. Yeah, thank you.
Okay, we're out of time, so let's thank the speaker once again.